Let's wait for a couple of minutes to let everybody join in, and then we will start. Let's wait for some time to let everybody join in, and then we will start. Okay, so today is the seventh session out of the 12th session that we are going to perform. I mean, we do for this. This is the seventh week of the course. noc25 bt19 Enzyme Science and Technology, which is taken by Professor Vishal Trivedi of IIT Guwahati. I'm Sanket from Kusuma School of Biological Sciences, IIT Delhi. So today we will be talking about the enzyme catalyzed reactions. And let's see what we have. So as we all know that enzymes are made up of proteins and they are a polymer of amino acids. So multiple amino acids, just give me a moment. Yeah. Multiple amino acids, they form a polymer like this. That forms a peptide, and that peptide forms a protein. So this is how it looks like. Okay. And the substrate and towards substrate and products, an enzyme is very specific. We've already studied about it. Within an enzyme, if this is an enzyme and this is where the substrate binds to, this area is called an active site. So active site is the pocket where the substrate binds. And the molecules which are produced by the reaction after the reaction is over is called product. And the enzyme activity can be modulated by non-substrate molecules, or they're called as, I would say, known as allosteric control, right? So if, for example, if there is something else that can bind here somewhere else and can regulate the enzyme activity, that is called an allosteric regulator. So we'll talk about these in specific when we will be studying about enzyme substrate kinetics. But anyway, about the specificity of enzymes. So there, the enzyme substrate specificity is due to three reasons. One is the geometric complementarity. What does that mean? So that is basically the lock and key mechanism as we know. So if this is the enzyme, and this is the substrate. If this is the enzyme and this is the substrate, they possess a geometric complementarity that makes them an ideal fit for each other. Otherwise, let's say if a substrate, let's say, is like this, is blunt ended, it will not fit with the enzyme. So that is the specificity comes due to geometric complementarity. There is electronic complementarity as well. For example, for DNA binding enzymes, for example, if we talk about polymerases, all the polymerases, most of the polymerases, they are positively charged, whereas DNA or RNA, nucleic acids, they are negatively charged. Fine. So this is one thing. And then there is stereospecificity also. For example, enzymes like alanine racemase, or there could be other enzymes um, also which only act upon specific, stereo conformation. Fine. So this is how it looks like. Now, talking about okay, the chromatographic techniques, as we already know these interactions specifically. So again, to understand the interactions of enzymes and substrate, there could be chromatographic techniques. So we have techniques like ion exchange chromatography, where the interaction between two different ion set of ions we can actually figure out. There are other chromatographic techniques also like gel filtration that can also tell you the interaction of your enzyme of interest with the substrate. It is possible to get to it through gel filtration as well. Other techniques which are very widely used could be like ITC. We'll discuss about it. That is isothermal titration calorimetry. So this technique basically will look at the heat generated or adsorbed due to the interaction. So we can study interaction through this. The another method which gets very widely used is SPR, that is surface plasmon resonance. Apart from that, we can use techniques like, let's say, UV visible spectroscopy as well. But these are they have a very limited, you know, range of detection. We really can't figure out a lot out of it. But anyway, these are some of the techniques, and we'll study about it. So for ion exchange chromatography, what happens is, let's say the reasons here, or I would say the column, is either either it's positively charged or it could be negatively charged. Okay, let's say if it is negatively charged, then only the positively charged proteins will bind. And at different, pH, so we can change this charge configuration by adjusting the pH of, you know, mm, the buffer. So basically, for a protein, there is something called the isoelectric point. This isoelectric point is the pH at which the protein has a net zero charge. Now, based on this, if we lower the pH or increase the pH, we can actually get the protein in, more negatively charged or positively charged, whatever. So based on that, the positive charge, let's say the net positive charge will bind, and the ones which has net negative charge, they will flow through. This is the principle of ion exchange chromatography, and one of the most studied methods, I mean enzymes for these, is the DNA enzyme interaction using ion exchange chromatography. So let's say that is how we do it. So in a positively charged resin, DNA binds, and with this bound DNA, we add enzyme, and we see what is the binding. Now, then there comes gel filtration chromatography. Again, it has been discussed. It is based on the principle of the hydrodynamic surface area of protein or enzyme in this case. So let's say a protein has interacts and forms, let's say, dimers, then the hydrodynamic area is more than if it is, let's say, it's in a monomeric form. So based on the molecular weight, we have different eluent fractions. So the first one which elutes out after sample injection, let's say this is sample injection, has the highest molecular weight, and the last one has the lowest molecular weight, right? And based on this, we can actually calculate. Uh, so as we have already discussed about, how we calculate the oligomeric status of a protein. Through this method, we can also find enzyme substrate interaction as well. So usually substrates always have the lowest molecular weight. So substrate comes out at the end. The unused substrate comes out at the end, whereas the enzyme bound substrate would come somewhere in the middle, right? And the distribution coefficient, it's again for a column, for a packed column, it's calculated. It's the fraction of stationary phase which is available to the given solute. It depends on the gel and the size of the solute. So it is calculated as VE minus VO by VI. A KD value greater than 1.5 is considered to be good. If we do not have a good KD value or distribution coefficient, we will see graphs, for example, in this case, will merge with each other. So if we will see one peak and another peak, there is not really addition volume, and this is, let's say, absorbance. So we don't see a very differentiation of peaks because of low KD values in column. So in that case, we usually have to go for column regeneration. Or we might have to use a better column which works at the ranges of molecular weight. Anyway, that is not the scope of this. So we are talking about electrophoresis methods again. So now once you have your protein sample, apart from running it in chromatography, the another thing that can be done is electrophoresis. For DNA, we go for agarose gel electrophoresis, and it is very simple. Where DNA, as we already know, it's negatively charged. So there will be a DNA and the gel. So if these are the wells, they will migrate towards the positive charge. So based on their molecular size. And we have a ladder which actually tells you what is the size of your DNA. But in case of protein, it is a little bit more complex because proteins are usually do not actually have negative or positive charge as such. So for that, if your protein needs to be run with without changing its native form, we do not want to denature the protein, then we form native page. Page stands for polyacrylamide gel electrophoresis, right? So okay, so in native page, so it always looks like this. The gel casting setup, it always looks like this. This image has been taken from Biorad, and this is how they gel electrophoresis, polyacrylamide gel electrophoresis works, and it is also known as vertical gel electrophoresis setup because it is arranged vertically, as you can see. Fine, it's arranged vertically. And the direction of protein migration is always towards gravity, as you can see. Negative charge is at the top, positive is at the bottom, and that's how it works. So with native gel or in a native page, you would always find, you can find the interactions between protein and, or let's say enzyme and substrate, or you can also determine the oligomeric status of the protein. There could be protein-protein interactions as well, which can also be visualized. In case of SDS page, what we do, this is SDS stands for sodium lauryl sulfate. In sodium lauryl sulfate, it is used as a denaturing agent, and you will always get the monomeric form of protein. So in this case, usually what we do not see any kind of interactions. Interactions cannot be visualized in this form of a gel electrophoresis setup. In case of urea page, what we do, we have a gradient denaturation setup, and in that we perform a gradient denaturation, and then we visualize the gel again. Now, based on there are other methods which are there. Could be spectroscopic method, which is based on, let's say, electronic transitions which happen. So they like pi to pi star or n to pi. These are the kind of transitions, and they have a specific absorption spectra. And based on this is the principle of UV visible spectroscopy. There's Beer-Lambert's law as well, Beer-Lambert's law, which we'll also talk. Then there is nuclear transitions. For nuclear transitions, we have NMR to perform nuclear magnetic resonance, which we have already discussed earlier. Vibrations could be there. So vibrations between, let's say, CO bonds, CN bonds, there could be bending and stretching kind of vibrations, and these can be used for FTIR, that is Fourier transform infrared spectroscopy. Also based on rotation. So if you see the rotational angles, what we can perform is something like CD spectroscopy, or we can also perform SPR can also be used to see rotation. So this is the principle of a UV visible spectroscopy, and you can see the Beer-Lambert's law also. So there's a source of light which goes through a slit and a prism, and only a kind of light. So here, suppose of a wavelength, a particular wavelength, it only passes through, and then it goes from a reference cell and to a sample cell, with which we get different intensities at the detector, intensities of this light based on the absorption. So the absorption can be calculated as epsilon CL. So it is, again, this is called the Beer-Lambert's law. right? So absorbance is directly proportional to the length of the cuvette which you will use. So the length of the cuvette is what it will be directly proportional with, and it will also be proportional with the concentration. C stands for the concentration of analyte, right? And based on this, we get um, the this equation where epsilon stands for extinction coefficient. Fine. It stands for extinction coefficient. So if we have a fixed length, so let's say when we use a cuvette, we have a fixed length. So when that becomes fixed, we can actually find the concentration of samples using this very method. Now, in using spectroscopic method, the main absorbance of protein, it comes at around 280 nanometers, around 250 to 270 to be specific. And this absorbance is due to the tryptophan and tyrosine residues which are present in proteins. Whereas nucleic acid, they absorb strongly at around 260 nanometers. Again, there is also variation there. Based on this, we have a 260 by 280 ratio for nucleic acid purity. So when we have this value greater than 1.8 or something like that would actually give you pure DNA, right? We consider it as pure DNA. For proteins, we have this A260 by 280 ratio somewhere around 0.6 usually, but it can also differ. For proteins, it's not exactly defined. In case of isothermal titration calorimetry, it's used to measure a variety of biomolecular interactions. What we actually have, these are called cells, right? These are called cells which will have your buffer plus protein, right? And these are injections which will have buffer plus your ligand, okay, or the interacting molecule with the protein. And when you inject, the titrant is on the injection and the titrand is in the cell. When you inject small quantities of this uh, into the cell, what happens is there is a change in energy. There's a change in energy, which is actually calculated as microcalories per second, as you can see in the y-axis. And on the x-axis, you have something called time. So when you have this, you can see this is a reaction. As you can see on the left, this is how it looks like, right? So heat can be generated or it could be absorbed. It's basically a principle of calorimeter where it only measures the heat generated or absorbed in the reaction. So here you see a curve, your peak like this. This kind of a peak is basically um, it shows you. So there's some sort of saturation also at one point. This is a good actually ITCP curve. And based on this, you can find out the affinity of your ligand or substrate to the enzyme. So when you do that, affinity of substrate to enzyme is known as Km, if you know that, through Michaelis-Menten kinetics. Or dissociation constant Kd can be figured out using uh, a ITC instrument. Another thing that can be calculated is the binding energy. That can also be calculated. Sorry. Okay. Another way of studying interaction is called SPR, surface plasmon resonance, where you have a metal surface and then over it you have sample molecules. It's a label-free method. It's a surface-sensitive spectroscopic technique. There's a light source which strikes the surface, and based on the interaction, you will have difference in the resonance energies transferred, the light which comes out. So it's a non-destructive way of sensing your sample does not get destroyed. It detects binding of biomolecules into arrays of probes. Biomolecules rapidly monitors the dynamic process to a wide range of biomedically relevant interfaces. So in case of a surface plasmon resonance, we get a figure which is called as a sensogram, and this is how it looks like. It actually tells you about the association and dissociation of interacting molecules. All the curves actually come in after the analyte injection. So when you are injecting the analyte, you will see the association, and later you will see dissociation and regeneration as well. Specificity of binding, active concentration of molecule, kinetics, binding kinetics. Here also you can find dissociation constant or the binding constant, and the affinity can also be figured out. Okay. If talking about the applications, I think I had another slide in ITC. It's not here. Okay. The problem with ITC is that, okay, we have not covered it. So there are certain disadvantages also, because energy change or the heat generated due to anything else, due to two buffer compositions which are combining with each other, will also be taken into account. So it's a global method, and it doesn't actually tell you very precisely, you know, if it is happening just due to the interaction or there is some other kind of interfering agent. That is a problem. There is a problem of slow kinetics. If the energy released or energy gained is very slow, then also it's a problem in ITC. Cannot be detected very well. And then it only acts at optimum concentrations. Okay. So usually when we see protein-protein interactions or protein-substrate interactions, there has to be an optimum concentration of the protein and the substrate both for both of them to interact well and to be captured it in ITC. To figure that out, it requires good amount of optimization. That is also another problem with ITC. I think I didn't say that. But regarding SPR, it is applications if we talk about, it can be used to measure dielectric properties, adsorption process, surface degeneration or hydration of thin organic monolayers or bilayers, polymer films, adsorption, desorption kinetics of biomolecules, antigen-antibody interaction and epitope mapping. So antigen-antibody interactions are the most common interactions. So this is, let's say, antibody. And here the antigen binds, and these are called epitopes, right? These kind of interaction, this is also binding interaction, can also be studied. Lipid bilayers and tissue engineering are other examples. Let's come to the questions. The DNA binding proteins or enzymes eluted from the chromatography column by decreasing the ionic strength of elution buffer, applying gradient of increasing ionic strength, increasing the column size, or altering the temperature of the sample. So let's say what kind of chromatography will we use for a DNA binding enzyme? DNA binding protein would be an ion exchange chromatography, and specifically an anion exchange chromatography. So that is not important, but we'll have, let's say, a positively charged, yeah, anion exchange. Yes, I'm right. So if there is a negatively charged DNA, which is negatively charged, it can come in and bind to these columns, right? It can call column. What it asks you is, Now once DNA is bound, you can then add the enzyme here. And once the enzyme is bound to DNA, so if this is the DNA and this is the enzyme that is bound to the DNA, how are we going to elute this enzyme is the question. So if we decrease the ionic strength of the elution buffer, that's not going to help. Applying a gradient of increasing ionic strength. So if your buffer has more negative charge, right? It has a more negative charge, then the protein is supposed to come out of this setup and come to the elution buffer. So basically, you can increase the ionic strength. This is the right answer. Column size increasing will not change it. Even altering the temperature of the sample will not change it. Eluted fractions in the DNA binding proteins or enzymes from chromatography techniques are analyzed for the purpose of determining the size of DNA binding proteins or enzyme, adjusting the pH of eluted fraction, determining the concentration of DNA in the sample, or studying the binding properties of separated enzymes or proteins to DNA. Again, the same principle if we see DNA binds to it, to the column, and then there is enzyme. Whatever comes out in the eluted fraction, so if you see different peaks, what we actually get to know is the first peak, the last peak, or the second peak. So if there are two peaks and two enzymes which are coming out, we are actually, what we are knowing is the binding property of the eluent enzymes to DNA. This is what we are studying, right? The migration of protein SDS phase primarily depend upon the net charge, solubility in the gel matrix, pH at the gel interface, or the enzymatic activity. So again, negatively charged, and then we have something like these. These are wells. There is a resolving gel and a stacking gel. This is called a stacking gel. And here we have the positive charge. And your protein will flow like this. So the migration of protein does not depend upon the solubility. It does not depend upon the pH or the enzymatic activity, no. But it depends upon the net charge, solely on the net charge, because it's an SDS page. And due to SDS page, there is what we call denaturation of the protein. The amino acid that dominate the absorption spectra in the near UV region of proteins are aspartate and glutamic, tyrosine and tryptophan, histidine and arginine, asparagine and glutamine. Aspartate and glutamate, yeah. So as we've already said, that the near UV region at 280 nanometers, we have this absorption peak due to tyrosine and tryptophan majorly. The double beam spectrophotometer improves measurement reproducibility by reducing the intensity of incident radiation, using multiple detectors for increased sensitivity, exposing the sample to multiple wavelengths, or compensating for fluctuations using a reference cell. So double beam spectrophotometer has a reference cell where, gives two beams to compensate for fluctuations which can happen. Enzyme substrate interaction can be deduced from changes in absorption peak or shift in wavelength from the aspects of reaction yield, binding events, enzyme concentration, or substrate volume. Based on the binding events will be the answer. Reaction yield or enzyme concentration, substrate volume will not change it. The additional insights that can be provided by isothermal titration calorimetry beyond the binding affinities are molecular weight, reaction kinetics, mechanisms underlying molecular interaction, or structural details of biomolecules. So definitely we cannot know the molecular weight or the reaction kinetics as well from isothermal titration calorimetry. Structural details can also be figured out, but the mechanism underlying the molecular interaction, whether it is an endothermic reaction or an exothermic reaction, these kind of things can be figured out. As the titration is gradually performed, the isothermal titration calorimetry measures the concentration of ligands, pH change, optical density, or the heat change during ligand titration. It does not measure the concentration because concentration is fixed in the injection, right? pH changes is also not checked. Optical density is not measured. There is no detector, but the heat change is actually detected. Isothermal titration calorimetry quantify the binding strength between biomolecules, measuring the concentration of ligand required for binding, calculating the temperature changes during binding, analyzing the entropy or equilibrium binding constant. Binding strength is always found out through equilibrium binding constant, also known as the dissociation constant. That's why the D in the KD. So that actually tells you the quantification of the strength between the binding of biomolecules. Surface plasmon resonance is utilized in determining the binding kinetics between antigen and antibody by measuring the changes in temperature upon binding, detecting change in fluorescence emission, quantifying changes in the refractive index in real time, or measuring changes in the electrical conductivity. We actually quantify the changes in refractive index, electrical conductivity, or the fluorescence is not measured. Not even the temperature is measured. Temperature, for that we require ITC, not temperature, but the energy change. The kind of information that can be obtained through surface plasmon resonance in structural interaction studies is changes in pressure, affinity and dissociation constant, temperature variation, or molecular weight variation. So we can actually figure out affinity and dissociation constants. Temperature variations cannot be figured out. And molecular weight variation, for that, you need something called gel filtration chromatography. Dash lamp is used as a source of visible light in UV visible spectrophotometer. Is a deuterium lamp, tungsten, xenon, or halogen lamp. So the answer to this would be a tungsten lamp. It is used for UV visible spectroscopy. Which of the following is called electronic spectroscopy? Is it the infrared, NMR, UV visible, or rotational? So this is based on the principle of electromagnetic waves. In EM waves, we have the infrared, we have the UV visible, we have X-ray, and also sort of thing. So the main spectroscopic technique is the UV visible spectroscopy. The substrate specificity in enzyme that determines whether to bind with L type or D type in terms of sugar is known as geometric complementarity, stereospecificity, electronic complementarity, or covalent complementarity. So it's actually the stereospecificity. So it is specific interaction with stereoisomers. Fine. Which of the following have the lowest wavelength in the electromagnetic spectrum? Is it radio waves, gamma waves, infrared rays, or microwaves? So, so as we know, lower the wavelength, higher the penetration. So we can say a frequency is inversely proportional to the wavelength, right? This is also known. So the highest wavelength comes to infrared, right? After which we have radio waves, microwave, and then gamma rays. So gamma rays has the lowest wavelength, and gamma radiation is that's why the most harmful out of all radiations. So with this, we are ending today's session. We will meet to again next week. That is on 17th of March, the same time, 6 to 8 p.m. We'll meet again for another the session 8 of the interactive course. Which is enzyme science and technology. Till then, I wish you good luck with your assignments. Uh, have a very nice time. And if there are any doubts, now would be the time that you should ask. Okay, if there are no questions from your end, I would like to take your permission to end this session today. We'll be meeting again next week, same time, 6 to 8 p.m. And I wish you good luck with your assignments. Thank you.